So our present topic is propagation problem. So these are actually unsteady or time dependent problems. Typically we are given the state of a system at time t equal to 0, and our objective is to find out the subsequent states as time progresses. So, and these are also known as the initial value problems. The examples are unsteady heat conduction problem, wave propagation problem, etc. And a large class of transient problems are guided by this equation. So you are now familiar with this equation. So this part is same as what you get in quasi-harmonic equation, only these are the two extra terms where and where kt and ktt are greater than 0, and this is the boundary condition. These are the boundary conditions. Phi equal to phi bar, which is specified on gamma 1. So this is called the Dirichlet boundary condition, and this is kx del phi del x nx plus ky del phi del y ny plus kz del phi del z nz plus g xyz. Now g is also can be a g can also be a function of time, and h can also be a function of time on gamma 2 or s. I think we should make it s1 and s2. So this is s1. So S1 and S2, and this is the initial condition. The initial condition has also to be specified, that is initially all over the domain the value of phi must be specified, and if ktt not equal to 0, then del phi del t also has to be specified initially. So this is the initial state, and actually from this initial state the system evolves in time. So we know the finite element terms coming from this part. Up to this we do not know what will be the finite element terms for these two terms in the equation. So see we'll find out what are the finite element formulation corresponding to these two terms, the part of finite element formulation for these two terms. So here the field variable is a function of the space variables and along with the time variable. So here actually what we do, we discretize the space. That is, here the nodal values are time dependent. Unlike equilibrium problems guided by quasi-harmonic equation, which we have seen, there these nodal values were not dependent on theta on time. Now here the nodal variables are dependent on time. So only the space is discretized. So here I made a mistake. So here this only time will not be there. So this is a shape function into, and this is the nodal variable. So this is actually called partial discretization, that is space is discretized but time is not discretized. And if you use here in the Galerkin formulation corresponding to kt del phi del t, you have to weight it with respect to ni. So this is ni kt del phi del t, and del phi del t can be written as, so again I have made mistake, I don't know, this t will not be there, yeah. So now here you see when you take derivative when you take derivative with respect to time, this shape function will not get differentiated, but this being a function of time alone, this will get differentiated. So we have written d because it is only function of time. So this is this, or we can write this as this into dot. Now whenever you get repeated index, wherever you get repeated index, generally here in this course we assume that summation is implied over the repeated index. That means here you can omit this summation sign automatically. Since j is repeating, that means there is a summation over j, so you can omit this summation sign and write it like this. So the ijth term, that is ith row jth column term, is kt ni nj d omega e, where this ij, you can write it like this. So I take I equal to 1, the first row, then j varies, so this, and take I equal to 2, then j varies, take I equal to 3, j varies. So this is the matrix kt. So, and for the other term, which is ktt del square phi del t square, so this is nj phi j double dot d omega e. So here again nj will not get differentiated, only phi j will get double differentiated, and summation is implied over the repeated index. So this is the KTT matrix. It is same as this KT matrix, only this coefficient KT has to be replaced by KTT. So now the equation is something like this. So these are the two added terms. And these terms are same as what we got for quasi-harmonic equation. Now you know what is KTT matrix. This is this. What is KT? This is this. And Kij and K, the actual original K which we got in case of quasi-harmonic equation is this. Ks2, that is what is coming from the S2 boundary, is this, and this should be non-zero if the element does not have a S2e boundary. So this is S2e. So this is again S2e, right? And this is the forcing term. So this term will be 0 if the element does not have S2 boundary. So this is the finite element. These are the finite element matrices, and this is the finite element equation. So now we'll look at some 1D examples, like vibration of a loaded string. So this is a string which is loaded with a force Fxt. So this is a transverse force, and the string is loaded with that transverse force. So this is the string, and here if the string deforms like this, then this is phi, this is this angle is, this is phi, this deformation or displacement is phi, this is phi at x plus, this is phi at x, this is phi at x plus dx. This is a time function, so phi x t. So phi is actually a function of x and time. So this is the slope del phi del x, and this slope is del phi del x plus the rate of increase of del phi del x into dx. Now t is always along the tangent. So here this is the tangent at this end, and this is the tangent at this end. The tension remains unchanged. Here the assumption is the tension in the string remains unchanged. So the force in the upward direction balances F dx. So if you do that, then this is the equation. This is a downward force, and this is a downward net downward force, and that is if you take the downward direction to be positive, and this is the mass of this. This is the mass of this part, where m is mass per unit length into dx. The total mass of this into del 2 phi del t2 is the acceleration. So you get this equation, or if you write it like this is this equation. Here kt equal to 0, but ktt is not equal to 0. So here you see that if you write an equation in this form, or if you get an equation in this form, a this and this, then if b square minus 4ac is less than 0, then it is elliptic, and if this you get parabolic, and if it is greater than 0 you get hyperbolic. So here you see you compare this term with this term and this term with this term. So b is 0 here, so b is 0, a is t by m, and here it should be c is minus 1. So this c is minus 1. So this is c actually. So this is c. C is minus 1. So b square minus 4ac is 4t by m, which is greater than 0, which shows that this is hyperbolic equation. So propagation problems are actually hyperbolic problems. So here axial vibration of a bar. So this is a bar, and which is given a load f xt, and here displacement at this end is u. So in place of u we are taking it as phi. Phi is a function of xt. So here if you cut this portion and show the forces, so this is sigma a, this is sigma plus d sigma a, and that means if you write down the, and this is f dx, force equilibrium equation, this is the net force in the right hand direction, and if you take this as to be the positive x to be the positive direction of phi, so this is phi double dot here. So m dx is mass of this, where m is mass per unit length. So this is the equation. So now you just write it like this. So del sigma del x is actually a e del epsilon del x, and epsilon is del phi del x. So we'll write it del because other than x there is a time variable here. So we'll not write d, it's better to write del. Good. So now you get this equation, and again you see this is a hyperbolic equation. But if you see the unsteady heat conduction problem, so one unsteady one dimensional heat conduction, so heat is entering the slab and leaving the slab here, and heat is flowing only in one direction. So in this direction it is infinitely long. So now if you take a portion here which has a cross sectional area, that means this length into the length in the depth direction as a. So then minus k del phi del x is the heat coming in, and minus this, that is del phi del x plus rate of increase of del phi del x into dx is the heat going out. So find out the heat which is staying in, plus this is the generation term. So this is the heat staying in, and this is the heat getting generated. So is equal to the mass of this. Mass is the volume. This is the volume AdX, and rho is the density. So it is the specific heat into del phi del t. So if you do this, then you get an equation like, if you do the simplifications, then you get an equation like this or like this. And see here del 2 phi del t2 term is not there, but del phi del t term is there. So you cast it in this form, and here you see a equal to 1, b equal to 0 and c is also equal to 0. So b square minus 4ac is 0. So this is a parabolic type of equation. So heat conduction problem, unsteady heat conduction problem, we have seen it's parabolic, it's of parabolic nature. So here we'll be going through an example of unsteady heat conduction problem. We have taken a two linear element mesh. So N1 is this and N2 is this. So here the boundary condition is 0, boundary temperature is 0, and this is the initial condition that at time t equal to 0, this is the distribution of temperature. So this is the equation. So now what you do, so you just during finite element formulation using Galerkin's principle, you use the weighting function ni. So you multiply ni with this and ni with this and you equate it to 0. So here this is the boundary term minus this is actually integration by parts, which you have already seen. So minus this is this. So this is the boundary term, this is coming from this, and this is the term corresponding to this. Now you actually here what you do in case of del t, so you assume t is equal to this. So this is again partial discretization, that t is broken up into, this is the space function and this is the time function. So nodal variables are function of time. So if it is, since it is a two node element, so this is n1 t1 into t2, and when you differentiate with respect to t, so this is getting differentiated, this n is not getting differentiated because n is not a function of time. So it is like this or this. So you put here you put this nj tj dot. So here you put nj tj dot and you get this term, and this is same as what you get in steady state heat conduction. So same term, sorry, this is not kT, this is k. So here I have made a mistake, this is not kT, this is k. Yeah, this is correct. So now so for n equal to 1, this is n equal to 1. So at LE n1 is 0, at LE that means at this point n1 equal to 0. So this term goes, this term remains. So minus n1 k 0. So n1 is also 1, you can make it 1 also. I have kept it n1, but you can make it 1. So this is actually the left end. So and this is the right end of the first element or the middle of the assembly. So this term is this. So and here for I equal to 1, this term goes, this term remains, which is this term. Here I equal to 1, so del n1 k, and here j varies from 1 to 2. Here also this is 1 and j varies from 1 to 2. So you get this and this. Actually this is, as you know, this you have already seen, this you have already seen for steady state heat conduction. Here this is actually from kT to this is actually n transpose n dx and kT you take the integral. This is actually NING means n transpose n. dx. That is this one. This one is also actually n transpose n. So this is actually n transpose n. This is n transpose n, isn't it? So this is n transpose n. That means if you take n as n1 n2 like this, then n transpose n is actually, transpose means it becomes like this into, so if you now multiply you get this. So this is nothing but n transpose n. So this is nothing but n transpose n. So you remember this is nothing but n transpose n. So if you write that ktt, the other way of writing this is ktt is omega e ktt n transpose n d omega e. So remember, so this is same thing. This is two different ways of writing the same thing. So now if you do n transpose n actually, then you get this. Or you can separately integrate n1 n2 dx, sorry, n1 n1 dx, n1 n2 dx, n2 n1 dx, and n2 n2 dx, then also you get this. So this is what you get from element 1. Similarly you get for element 2. So for element 2 actually this is the middle and this is the right. So now while assembling, here this middle end and this middle end, they get cancelled out. This middle end and this middle end, they get cancelled out. So this remains and this remains. So this is 0 and this is the assembly of the matrices. But since the boundary conditions are given as zeros, the first and third, the T1 and T3 are given as zeros. So the first row goes, and for this the first column goes, and for this first column goes. So you get this equation, the single equation you get in T2. So this is the equation which you get, where T2 at t equal to 0 from initial condition is x into L minus x. So put x equal to L by 2. So this is the initial condition. So this is actually the ODE. Now in the next video we'll discuss about the solution of propagation problem, the finite element formulation which we have got, how to solve the equation. So let us stop here.